So our third speaker of the morning is from Synopsys, our platinum sponsors for today, Wai-Hua Han, who's going to talk about acceleration of complex RISC-V processor verification using test generation integrated with hardware emulation. Another key theme that you'll see today is the is RISC-V. A lot of companies, and I know a lot of companies in Austin, are moving over to RISC-V. So we're trying to speak a lot about RISC-V verification as well. So Austin's been very, very well known for CPU verification, processor verification, but now a lot of people are moving to RISC-V for obvious reasons. Wai-Hua Han is a senior architect and application engineer at Synopsys Protocol Solution Engineering Team. He graduated from Beijing University of Post and Telecommunications with a Master's of Science degree. For over 20 years, he has been working on different aspects of functional verification with simulation and hardware-assisted verification. I'm not sure I've done an abstract for your talk. Okay. There's no abstract that I can see, so I'll go straight over to you. Okay.
Thank you very much, Mike. Everybody, good morning. Yes, as Mike mentioned, I have been an AE, application engineer in Synopsys for a long time. I started with System C, System Verilog, UVM, portable stimulus. Now I'm working on a solution with different team in Synopsys. It's kind of hardware assisted test generation dedicated for RISC-V. So this kind of solution is actually covered in today's slides. I hope it may be some helpful for your daily job. Every verification engineer, I mean, I'm working on verification for a long time. Every verification engineer actually has some challenges every day. Performance is one of them. They always want to have a better performance. The next one would be how I can generate a high quality test vector. There are different solutions, different methodology like UVM, portable stimulus. That's another one. Last one, but not the least, productive debug solution. Those things are commonly challenges for the verification engineers. And I hope the solution we discussed here and we develop here may be helpful, partly helpful on these challenges. So let me go ahead and report what we implemented dedicated for RISC-V. So RISC-V, if you look back, 2010, I think is the first release of RISC-V from Berkeley University. After that, if you look at today, if you look at the typical RISC-V design, it's much, much complicated compared with the first release 15 years ago. There are so many extensions, vectors, hypervisors, different floating data support, etc. You can also see virtual memory is popular now in common RISC-V design, MMU, TLB, PMA, PMP, all this kind of fancy stuff. But that's a challenge for verification. Introducing cache, L1, L2, system level cache, all those kind of stuff. Interrupt, multi-hot, multi-issue, out of all the executions, all those kind of fancy processor technologies you can see now in current RISC-V design. I will show you in next slides what a typical RISC-V design we can see from the open source. So that's a challenge for verification, and some new requirements or challenges for verification. First, we need to have a very high throughput performance solution. Second, for the test vector, you need to really understand deep understanding about the different extensions or different design aspects, then you can generate the high quality test. And you need really running a long test if you want to catch some difficult scenarios, especially when you think about the cache. We'll discuss a little more later. And I also mentioned the execution platform or performance platform solution. Is simulation still good enough to address your challenges? So there's a number. How many cycles do you need to run to validate our current modern processor? 2 years ago, in RISC-V Summit 2023, I think, CEO, the Impera's CEO, if you're working on the RISC-V design, you may know this company is also bought by Synopsys now. Simon Diamond mentioned that you may need to run around 10 power 15 cycles to get a kind of high quality validation for your processor. So think about you need to run so many cycles to test to verify your processor. Xiangshan is a RISC-V project. You can find this project from GitHub. It's an open source project. It's a high performance RISC-V processor. It has many features we just mentioned. It has MMU. It has iCache, Dcache, L2 cache, the advanced interrupt, supports vector, RV64. And look at the block diagram of the design. So many things for very engineer you need to test. Standard test about all the instructions you may need to verify, cover all the instructions. And maybe more important is a microarchitecture in your design. You have your priority cache implementation, how to verify those macro architecture. Those are really big challenges for RISC-V processor verification. Sting. Sting is a test generation solution. Synopsys bought it maybe 2 years ago. It generates a high quality random instruction based on a bare metal software program. It's a software-driven methodology for RISC-V design. It has different kinds of test generation technology used in it. Randomization, pure randomization to generate different instructions using different registers, different workload. There's like the litmus, etc. Dedicated test. Many times, designers want to develop some direct tests for my architecture, my design, and those real-world scenarios, true sharing, false sharing, all those things you can find from Sting. It's a self-checking program, a test. So you run it, you will know it's pass or fail, although it's random. It supports all the extensions now in the RISC-V. So it has more than 100,000 tests. Many users, actually RISC-V users, are using Sting now. For advanced RISC-V, to verify that, only cover all the instructions is not enough. Only cover the instructions to using different registers in your instruction is not enough. Only cover this instruction, load instruction, followed by another instruction is not enough. If you want to verify the complex implementation like the Xiangshan product, you need to really run a lot of long tests to cover the scenarios, cover the microarchitecture design. At least some of them, think about you have multiple core, think about you have different layer of the cache, data cache, instruction cache, etc. For example, algorithm, you need to think about maybe spin lock, ticket lock, all this kind of exclusive access. You may think about atomic instruction, those things. Ordering famous litmus tests, fans, all those kind of stuff. You may need to run them on instructions, on different ISS's orders, some cache-related tests. We just mentioned the true sharing, false sharing, cache evasion, all those kind of stuff. All those kind of stuff, you can see they actually need a long test. When you run true sharing test, doesn't mean, okay, I pick up one cache line, all the processor or the hearts trying to access this cache line on the same address. That's only a simplest scenario for true sharing. If you want to really access all the microarchitectures for this cache management in your design, you really need to run this cache-related tests over and over, maybe forever to run it to catch some corner cases for you. So that's really need a high-performance solution, run those tests many times and long tests. So based on this requirement, we develop a new solution. We call it the hardware assistant test solution for RISC-V. What means hardware assistant verification? That means, basically, it means that take your RTL, synthesize it, put it into Synopsys emulation or HAPS system, run it in an emulation that will provide a much higher performance compared with simulation. I will give data in the next slides. And at the same time, this test generation, we will use Sting to generate this silicon proven solution, generate a high quality test, but not like the traditional way. You generate a test, you run it, generate another test, you run it. We want to provide a much better performance, much better syrup compared with the traditional usage with Sting and ZBoo, and generate many tests in parallel. And instead of generate tests, load it to ZBoo or load it to your emulation, then done, generate another one, load it, and you check the result. What we want to do is that we want to maximize the parallel from both test generation, emulation, and the integration of test generation and the emulation. Here is how it works. This is Sting. You can run, Sting has a feature called Sting regression management. It will generate many tests. And you can run SRM, Sting regression management, on a computing farm, 4, 5, 6, 8, as many as you want. Each of the Sting will generate a test, many tests. And so you will generate a lot of tests from on the computing farm. Then we develop a streaming interface here. We will pick up the tests from your computing farm and load the test to ZBoo or hardware, emulation hardware. What it's doing here? Inside the hardware platform, we have a test management. This test management has a protocol, a handshake with a streaming interface. Basically, that's a part of a test bench. And it will tell the streaming interface, I need more tests. Then the streaming interface will load one test to your design and load another test one. When the first test is running, we continue to load tests to your hardware. And until we occupy all the memory you are available. And this may run faster, this may run faster. There's a synchronization between them. When all of the tests is running, it's done. We'll come back and we will wait to load more tests. So basically, this is how it works. Certainly, we need to output the results. In the result, you will see which test is passed, which test failed, and you can debug your test when it's failed. So you can see this is a high performance hardware assisted test generation and validation for RISC-V dedicated. About the performance, first, let's look at the emulation compared with simulation. We are actually using that Xiangshan as a reference design, 4-core Xiangshan. We are running multi-million cycles for each core. And for simulation, it's finished in around 5 to 6 hours. And when we run the same string, that's a long string test. When we run the same test in the hardware, in the ZBoo, we finish in several seconds. You can see around more than 6,000 performance improvement when you move from simulation to emulation. This number can be different, right? When you have 8 core or 16 core, this number may be much higher than that. Now we move from the traditional emulation to this streaming method. We figure out running 70 string tests in non-streaming mode. Non-streaming mode means we generate test, we load it, we run it, and we shut down the hardware, right? That's the traditional way. Then you bring up the set up the hardware again, then load your another design and run it. And every time you have initialization of ZBoo hardware, every time you have a configuration for your design before you can really run your test, right? And in the natural mode, for the 70 string tests, we finish about in more than 1,000 seconds. And in the streaming mode, we finish less than 300 seconds. We see around 4x performance improvement. Please note that this 4 times is add on for this 6,000 times performance improvement in the streaming mode. And this is the reason why we can see the streaming mode may provide a better performance. We have some extra benefits. We can concurrently generate the tests and run an emulation. Not like before, you generate 1,000 tests, all the EFL stay there, and you run them one by one. So if you running tests besides the performance, you may see some other benefits with this flow. And I think that's maybe more important for verification engineer. The traditional way, when you do it, you generate the EF, you load it, you reset your core, you run it, you shut down your core, you shut down your ZBoo, and reset again. So every time when you run a test, it's from the reset state, a clean state, right? Now, you don't shut down when you move to another test, even move another round. It is possible you run forever for several days from this. You will have a very different state for the tests. and it will have a chance for you to catch some very corner cases bugs, architecture-related bugs with this streaming mode. That's another benefit beyond the performance we can see. But that's also a challenge. I will explain what the challenge is. Reproduce or failure is very important for very engineer. If you run a single test, you can almost make sure you can reproduce it if you run again. Now with this streaming mode, you don't know if you can reproduce them anymore, right? So in most cases, it's not something really, really new. You can see the similar idea from some other things. In most cases, if you rerun that specific test, if it's interrupt related or exception something, you may reproduce it. So just rewrite it one time. So in this our flow, we allow the user to specify, okay, I only want to run this specific test still in streaming mode. So the usage is the same. You run the whole streaming mode or you run specific test. We are using the unified interface to the user. And we hope it will help you reproduce it. If not, the next step is you may want to run this test multiple times, several times. You can specify how many times. It's still a chance you cannot reproduce it because this error or this failure may be related to the sequence you run the test, right? So we allow the user specify, we are in a YAML file, specify this is my target test is failed, but I want to rerun these tests and another 6 tests beyond this one, before this one. You can specify numbers. Then we will rerun these dedicated tests for you. Should you run 5? Should you run 7? Or maybe run 10? I don't know. And that's the way maybe help us to reproduce a failure in some cases. But this is the way we think we need to follow up to reproduce and debug a failure in case we see a failure. And you can see this is the result. In the sequence, we specify this R1. We will figure out before that we run this 6 and we run them one by one. And just as in the streaming mode. Yes, thank you. Now, another challenge I mentioned, but I did not discuss yet, debug. How to debug a test failure? Sting is a software-driven test because we generate the ELF for you. You can run it directly. It's not like UVM or etc. And so if when we debug a failure, I work with different team, even our internal team, like ArcFile, RISC-V team. Software engineer usually debug it like the GDB, right? Not GUI or not GUI. They set a breakpoint on the function, on one of the instruction, etc. They look at the register. They run it step by step. They look at register if this is expected results. So when I developed some tests before for ARM coherence, I'm doing a similar. That's how software look at the debug the case. Hardware analyze. When I work with our RTL designer, they always ask me, okay, given the waveform, I will look at it. They look at the waveform. They look at like the status of the register, etc. But to debug software-driven tests like the Sting, if we can look at both from the view of software and the view of hardware, and we can bundle them together, integrate them together, so that will provide us a very high efficient debug method. And I'm actually using this method for, I already integrate the setup this three method for Synopsys ARM core, as well as for the open hardware core. That's also a famous open source. I'm using this one. For internal Synopsys, I can get help. Every time when I have failure, I can get help, either software team or hardware team. But work on those open source one, I really cannot get any help. I look at source, I look at the waveform, and these are synchronized to each other. Every time step by step, I can see the waveform change. By the way, this is a post simulation debug, so you don't need to rerun the simulation. You can run it many times. You can forward, backward. And then when I move to the hardware, when I look at click on this hardware, I can see the driver. At the same time, I will see what the instructions are running at this time. Who are running to this memory? Which instruction running to this memory? It is about multiple core. So if you have multiple core support, you can see each core, what are they doing at this moment. This will provide a very high efficient debug capability. And when I show this to our ARC team, they immediately realize the capability of this one, and they help me set up this same flow in our ArcWave team. So future development, in Paris is another thing popular in RISC-V world. We're thinking about to integrate in Paris fast processor model and tracking in this flow. And we want to integrate functional coverage. And we want to provide a better performance. We know some places we can still work on it and provide even better performance on this flow. Debug automation. I just mentioned the debugability of Verdi hardware software. Think about a scenario like this. You are running the regression during your nighttime in the streaming flow. We know your test failed, right? If we can rerun this test immediately, and dump the waveform you specified in case of failure test, you can dump this trace log, you dump the waveform. Now, in the morning, the engineer comes to office, see a failure. He already have the trace log, he already has a FSDB, so he can debug it immediately instead of rerun the tests and regenerate this trace log, etc. This is something we want to implement. We call it debugger automation. Those are some things in our head, and we want to do in the future. Okay. I think this is broken.
Okay, we're finished.
One last slide as a summarize. Okay. The summarize. We hope this hardware assistant test generation solution will provide you a much better performance and a very shorter turnaround time for the regression, etc., and a high quality validation for your tests. Second, Sting generation. Sting tests, we want to run the Sting in the parallel mode. And so you can generate as many as tests to feed into your high performance hardware system platform. Okay. And then debug. Last but not least, this is really important. Every engineer wants to have a high performance, high efficient debug ability. And the solution we provide here, I hope it will be helpful for the engineers' daily work. Thank you.
Thank you. Thank you. Thank you very much.